Okay, today we're going to be working on forces and compounds. So in this picture here, we have water molecules, two water molecules, and within those water molecules we have bonds. But this dashed line shows something we haven't gone over yet, which are called intermolecular forces. And that means forces that exist between two different molecules. So intermolecular forces occur between molecules, and intra, which is referring to those bonds in that picture, are forces that occur inside molecules. So we're going to be going over different types of intermolecular forces. The weakest of them will be the van der Waals forces, and this includes London forces, which are dispersion forces. And then we also have dipole-dipole interactions. The next force, which is a little bit stronger, are ion-dipole interactions. An example of this is salt dissolving in water. And then the strongest type of intermolecular force are hydrogen bonds. So dispersion forces, London dispersion forces, were named after a guy named Fritz London, and this is a picture of him here. And like I said, these are the weakest of all molecular interactions, and this results from temporary shifts in the density of electrons in the electron clouds. So here we have an atom where the electrons are symmetrically distributed around the nucleus. And here we have a temporary shift of the electron density to form a slightly positive and slightly negative end. And this will occur when two atoms approach each other. And this can occur because electrons are in constant motion and electrons have charges, so they're either repelled or attracted, depending if a negative charge approaches it or a positive charge approaches it. So I'm going to show you guys a video that will illustrate this much better than I could do just with some pictures, and then we'll be going over it in more detail.
Mr. Anderson, and this is Chemistry Essentials video 16. It's on London dispersion forces, which were first identified by Fritz London. That's where they get their name, after this whole idea of quantum mechanics had been developed. Can you find him in this picture? He is right here. But before we move on and talk about it, think about the forces in this picture. Which are greater, the forces within the individual people holding their atoms together, or the forces between them holding them together in this photo? Well, clearly it's the forces within your body. And so this is the first video in a set of videos that talk about bonding between molecules and within molecules. And so if we think of them all as molecules and we move them apart a little bit, there are going to be the intermolecular forces. Those are going to be the forces between the molecules, between this molecule and this molecule, and between this molecule and that molecule. And these are generally going to be really, really low compared to the intramolecular within the molecule itself. And we'll talk more about those in later videos. But London dispersion forces are going to be attractive forces. These are intermolecular between molecules. And they're going to be found in all atoms and molecules. So everything is attracted through London dispersion force. It's really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole. Those are going to be a molecule that has a charge. It has a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also as we increase their polarizability, which is going to be the squashiness of a molecule. Generally, the more electrons you have, the higher this is going to be. And so as we increase molecular size, we're going to increase these dispersion forces. And finally, pi bonding, which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase these. And so let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase is going to be these London dispersion forces. So right here I have two helium atoms, and so they're going to have two protons on the inside, two electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. And so what this really is creating are two what are called temporary dipoles. They have positive and negative ends. And so a London dispersion force is simply going to be the connection between those two. It's fairly simple. It's going to hold them together. Now, it's just instantaneous. It's temporary, and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get that. So what's going to increase these London dispersion forces? Well, contact area is one thing. The more electrons we can have closer to each other, the more of these forces we're going to find. So if we look over here at N-pentane and neopentane, they're both going to be made of the same atoms. But these ones right here are going to be looking more like a column and these more like spheres. And as a result, these ones are going to have more surface area, more contact area, so we're going to have greater forces. And so the boiling point of N-pentane is going to be higher than that of neopentane based on these London dispersion forces. What else? The polarizability. And polarizability, remember, is the squashiness. The more electrons we have, the more forces we're going to have. And so this right here is a protein. Proteins are massive in size, and a lot of that three-dimensional shape comes from these London dispersion forces. Also, it's going to explain why as we go down in the periodic table, let's look at the halogens right here. Halogens are going to have the same valence electrons, but as we go to fluorine, chlorine, bromine, and iodine, we're actually going to go from gases, fluorine, chlorine, to liquid bromine, and then solid iodine. And that's all going to be based on these London dispersion forces. As the atoms get bigger, they have more electrons, we're going to have more of this uneven electron.
Okay, so from the video, the London dispersion forces are the attraction between nonpolar molecules or between two atoms. And this is the only attraction force for nonpolar substances. All molecules do display dispersion forces. And what you saw in the video is the more electrons, the stronger the London dispersion force. So if we look at these three examples down here, to figure out which of these has the strongest London dispersion force, what you need to do is to get out your periodic table and look at the count the number of electrons in each one of these atoms or molecules. So I want you guys to do that now. And then we're going to go over which one has the strongest London dispersion force. Okay, so if we look at fluorine, fluorine is diatomic, and fluorine by itself has 9 electrons, but if we have a diatomic molecule, that means we have 18 electrons. Neon has 10 electrons. And then finally, carbon has 6 electrons, and each of those hydrogens have 1 electron, so that has a total of 10 electrons also. So the one that would have the strongest London dispersion force would be fluorine because it has the greatest number of electrons. And that's how you would determine if you had a choice, like which would have the strongest London dispersion force, is by looking at the number of electrons. Okay, so this is just more of a picture of kind of what they were showing in that video, is that if you have a molecule or an atom by itself, the electrons are distributed very symmetrically around the atom or molecule when we're talking about a nonpolar nonpolar molecule. However, if the atom or molecule approaches another atom or molecule, the electron clouds in each of the atoms or molecules are either attracted or repelled by each other. So these dotted lines represent the very symmetrical electron distribution when there's nothing else nearby. We see that as these two atoms, or in this case molecules, approach each other, the electron cloud that's closest to the other molecule in this case is attracted to that nucleus in the other molecule. So it's kind of pulled towards that nucleus in the other molecule. And then this, the electron cloud on the other side of that molecule is being repelled by that approaching electron cloud. and it's being pushed away. And this creates a slightly negative end of this molecule because of the attraction between the electrons in that nucleus, and a slightly positive end because of that repulsion of the electron cloud by that electron cloud. So we end up having slightly negative, slightly positive ends on both of the molecules here. So we see this, and as the number of electrons increase, the more electrons we have, we get a larger slightly positive and larger slightly negative ends in the molecules, and we have a stronger London dispersion force. And like you was saying in the video, this occurs because electrons can move around, and they will move around either as they're attracted or repelled, depending on the situation. So here's kind of another animation to help you see this. So here we have two neon atoms. So initially, they are very symmetrical, but as they approach each other, the electrons are attracted. The electrons in this neon atom are attracted to the nucleus in the other neon atom. The electrons in the other neon atom are being repelled by those electrons that are moving closer to that neon atom. And this creates a slightly positive and slightly negative end on both the atoms. And like he was saying in the video, this force is going to be more noticeable at very cool temperatures where the atoms are moving more slowly, and as the number of electrons increase or the contact between the two atoms increases. Okay, and what he was also showing you in the video is that these forces kind of explain the states of matter we see with the halogens. So fluorine and chlorine have very few electrons. They have very small London dispersion forces in comparison to other halogens, and these will be gases at room temperature. We look at bromine. Bromine has more electrons, and it will have a more noticeable London dispersion force, and this is a liquid at room temperature as a result. And that's a picture of bromine over here. Iodine has a very large number of electrons and a much more noticeable London dispersion force. So it's going to be a solid at room temperature, and this is a picture of iodine down here. So that can all be explained by these London dispersion forces. Okay, so now I want to show you an example of the London dispersion forces in nature. So if we look at this gecko, geckos can climb vertical surfaces like many different lizards. And if we look at their skin, what we see is that there's a lot of surface area on their skin. And these are all composed of like nonpolar molecules. And they are also climbing something that has a nonpolar surface. So those two surfaces, the surface on their skin is attracted to the surface of the leaf that it's climbing and allows it to climb that vertical surface. Okay, the next type of van der Waals force are dipole-dipole forces. So polar molecules will have that London dispersion force we just went over, and on top of that, they will also have a dipole-dipole force. So if we look at a bunch of polar molecules, they all have partially positive, partially negative ends on each of the molecules. And those partially positive, partially negative ends are all attracted to each other. And that kind of holds those molecules together. And in a lot of cases, this will end up making the polar molecules a solid or sometimes a liquid. So that's a dipole-dipole force, which is another type of van der Waals force. The next strongest type of intermolecular forces are called ion dipole forces. So these are very specific forces that will be present when we have something that's ionic, like sodium iodide, dissolved in a polar solvent, for example, water. So in this case, sodium is a cation, and it will be attracted to the negative, partially negative end of our polar solvent. Iodine is an anion, and it will be attracted to the partially positive end of our polar solvent. So I'm going to show you guys a video, a simulation, to help you to see how this occurs. And also, this is why ionic compounds will dissolve in polar solvents, is because of this ion dipole force. Okay, so I'm going to stop sharing for a minute and pull up the video. So what I want to show you with this simulation is the dissociation of sodium chloride or table salt in water and how the intermolecular forces help facilitate this. So in this simulation here, what you should see is this is sodium chloride. The green ions are your chlorine ions. The white ions are your sodium ions. You know, so chlorine ions are larger because they're negative. Sodium ions are smaller because they're positive. So here we have salt being added to some water, and then we're going to watch what happens as it dissolves. So the water molecules have partially positive ends on the hydrogen ends, and these are attracted to the slightly negative or the negative chlorine ions. We have the partially negative ends of the oxygen on the water molecules being attracted to this positive sodium ions in our crystal. The water molecules then, as they're attracted to the different ions, pull those ions out of the crystal, and then that is what slowly dissolves the crystal in water. So here we see the water molecules attacking all those ions in the crystal, and this results in dissociation of our sodium chloride in water. Okay, so what I want you to do now is to figure out what kind of intermolecular forces we've been talking about, and that is the London dispersion force, the dipole-dipole force, or the ion dipole force, what exists between the following molecules. Now to do this, what you need to do is you need to determine if these molecules are polar or not. If they are nonpolar, then all you have is the London dispersion force. If they are polar, then you have the London dispersion force and you have the dipole-dipole force. In order to consider ion dipole forces, you would have to have two molecules present, one of which were an ionic compound, and the second would have to be a polar compound. So in this case, we only see one molecule in each case, so we can't have that ion dipole force. So just pause the screencast for a minute, draw your Lewis dot structures, figure out if they're polar or not, and then if they're nonpolar, you just have London dispersion force. If they are polar, you have London dispersion force and you have dipole-dipole. Okay, so hopefully you guys tried that. So let's look at these. The first molecule is a polar molecule because of the electronegativity difference between hydrogen and bromine. So this will have dipole-dipole forces, and it will also have dispersion forces. Second one, if you drew your Lewis dot structure for that one, you should have seen it's very symmetrical. So it's going to be nonpolar. So this will only have dispersion forces. The third one, if you drew the Lewis dot structure, what you should have seen is that you have a lone pair on sulfur. This makes it a polar molecule because it's very asymmetrical. And as a result, you will have dipole-dipole forces, and you will also have on top of that dispersion forces. So every molecule will have dispersion forces. However, polar molecules will have also dipole-dipole forces. Okay, so I want to go over one more type of force, which are hydrogen bonds. So if we look at water, this table is showing you water compared to other molecules where we have hydrogen bonded to an element in group 16. So water is a very small molecule with extremely small molar mass compared to other molecules in the same group. But we see that water has the highest melting point. It's 0 compared to negative melting points of all of these compounds. It has the highest boiling point by far of all these compounds. It also takes the most energy to melt. So that's the heat of fusion, is referring to how much energy is needed to melt a piece of ice compared to other molecules in the same group. And it also has by far about 2,000 joules per gram, the highest amount of energy needed to boil this amount of water compared to other molecules in the group. So what we see is this is because of the hydrogen bonding that we see with water. So it has the lowest molar mass, but the highest melting point, the highest boiling point, the highest heat of fusion, and the highest heat of vaporization. So here we have water, just to show you what happens. And water has hydrogens and the oxygen. So that makes it a polar molecule because the hydrogen oxygen is very asymmetrical, and we have a partially negative end close to the oxygen and a partially positive end close to the hydrogen. So when we have water molecules near each other, what we see is that the partially positive hydrogen are attracted to the partially negative oxygen on neighboring molecules. And this results in hydrogen bonds. So here we have these attracted to the oxygens, and likewise over here. And then what happens is that you get a lot of cohesion and a high surface tension in water. And if you were to, if like in the summertime when it's warm out and you go swimming, you decide to do a cannonball, what you'll see is that if your stomach hits the water, it really hurts because your stomach is breaking all that surface tension on the surface of the water. So here we have a penguin that's going to go into the water and it's doing a belly flop, so that hurts. And that's because of that hydrogen bonding in the surface of the water. So there's hydrogen bonds there. And then we have our intermolecular forces and our intramolecular forces within the water molecule. So what we need to have a hydrogen bond is we need to have a hydrogen atom covalently bonded to a very electronegative atom. Typically, we see this with nitrogen, oxygen, and fluorine. You could have other elements, but it would have to be a very large difference in electronegativity. And we also have to have a lone pair of electrons on the very electronegative atoms. So here, fluorine has 3 lone pairs of electrons. So we then get hydrogen bonding. If we don't have one of these conditions met, there will be no hydrogen bonding. So here we have the covalent bonds in red and blue. And then we have our hydrogen bond in green. That's between 2 different molecules. So the hydrogen is attracted to the lone pair of electrons on the very electronegative atom on the neighboring molecule. So here is an animation showing that. Here's a bunch of water molecules. The partially positive hydrogens are attracted to the partially negative oxygens. And this is hydrogen bonding. So this is what creates the very open structure in ice and also in water, and is also the reason why ice is less dense than water, why it floats on water. So an example of how this plays in nature is if you think about certain water bugs can walk on water, and that's because of the very high surface tension on the surface of the water, and these water molecules are not breaking the surface tension and they walk on it. So what we see in conclusion is that the more intermolecular forces we have with a compound, the higher the boiling point, like we saw with water, and the higher the melting point. And that's because molecules are attracted to each other more strongly and tend to stay more as a solid or as a liquid.